Today, I'm going to introduce you with missing data in R. Previously, I had this workshop as multiple imputation in R, but here I will talk a little bit more about missing data in R. So I decided to change the name to missing data in R. The web page for the workshop is in the link that Andy sent in the chat. And you can click on the link and you can download the data set and also the HTML. If you like, you can also print the page HTML as PDF and save it as PDF. With that, I'm going to start the first slide of the missing data. Okay, so missing data is one of the most challenging issues that we might, as a data analyst, face when we try to analyze the data. There are a variety of methods that can handle missing data analysis. Some methods are ad hoc. Basically, you have some information or based on some method that are not precise, you can directly impute the data. There are some other statistical methods can handle missing data. In general, there are three main ways we can handle missing data in statistical analysis. One is ignoring the missing and dropping the cases that has missing on it. Other one is basically fill out the missing data with some values. We will talk about how we can get those values, but this is the general ways we can handle the missing data. Another way of handling missing data is embedded within the statistical analysis. Some statistical analysis, like full information maximum likelihood or EM algorithm, directly handle missing data without directly imputing them or dropping them. Depending on the type of the data, one of those methods might serve you. Depends on sample size or percentage of missing or situation that you have. One method could be better than the other. There is not definite method that perfectly handle missing data, and we're sure that we are doing that correct. But we try to handle missing data in a way that our statistical analysis don't give us biased estimates. Most focus of this workshop is multiple imputation. And I will talk about why this is important. This is a good method and reliable method of handling missing data. Some methods may not be sufficient for handling missing data. For example, dropping cases with missing data, you might lose all information or most of the information that you have. You might end up with not any cases that has complete all variable in your analysis. And also some methods like full information maximum likelihood may not be available for those specific analyses that you want to run. Multiple imputation, in the other hand, is very reliable, and these days is one of the most popular way to handle missing data, and it is implemented to most statistical packages. In some imputation method, we are able to impute the data in a way that the imputed value is plausible. So that's also another advantage of multiple imputation. In R, there are many packages that deal with missing data and try to handle missing data and help you. Currently, I checked there are 165 packages in R that deal with missing data. For list of packages, you can click on this link and you can see the ongoing project that R has and all the packages that is implemented in R. So, in order to handle missing data, there are some goals that we want to achieve. First is minimize the bias. So, for an example, if we want to estimate the average weight lost for people in a diet experiment, it's possible that men more likely refuse to respond to their weight loss. In this case, deleting basically missing cases will cause bias. So that might not be a good option for you to handle missing data. Another goal of handling missing data is maximize the available information that you have. Data is valuable. Sometimes you don't have many cases. So you want to use as much as information as you have. So again, dropping participant with at least one missing is not ideal in this case, if you don't have enough data available. The third goal of handling missing data is to get a good estimation of uncertainty. By uncertainty, I mean a standard error of the parameter that you're looking to estimate most of the time. That's one example. For example, you want to run a linear model. You want to get a correct confidence interval. So you are looking to find a method that can retain that uncertainty which associated with your analysis. So for example, if you impute the missing data with the mean of each variable, then you lose a lot of uncertainty. You might, if you have high percentage of missing. And that method is not ideal for handling missing data. So again, in summary, we want to minimize bias. We want to use all available information. And we also want to get a good estimate of uncertainty. So let's talk about missing data in R. By the way, if you want to copy paste some of the code, you can click on K, and then I actually disable. So if you click on the slides, it's advanced. If you want to prevent this to happen, you can click on K, and then by clicking your cursor, if you want to copy paste, it doesn't advance the slide to the next. In R, we use NA to for missing data. So if your data has something like 999, a lot of data has something like that. When you read the data in R, you can specify which string of variable you want to assign as NA. By default, the empty space or blank is going to be missing. for most of the reading function in R. So yes, I see somebody wants the link. Yes, it's up there. And Andy, if you can please, I will do. There you go. So let's see how R handle the missing data and how you can, it shows the missing data in your data set. If I write something like this as empty value, that's not the missing. So if you set A equal to empty or null, it will return null. Null is not missing in R, right? Missing is NA. So here I assign NA to A. And when I print A, I get NA. If I want to create a vector, or let's say a variable with 5 observations, and observation number 4 is missing, I can just type like this. And if I type NA, that 4th element of this vector is going to be missing. In R, there is a generic function isNA that indicate which element of object is missing. So you can run that isNA to a vector, and it tells you the position of missing that is missing. So if it's not missing, you get false. If is missing, you get true. So that means this is missing, right? The 4th element. If you want to identify which element in a vector is missing, you say which is NA, which gives you the number that is true. So it returns the place that you have missing. To get the total number of missing, you can run sum over that isNA, because this isNA is a logical vector with true and false. If you sum, it takes true as to be 1 and all the false as to be 0. And it gives you number of missing in that vector. Any NA is in the same family of isNA. If there is any NA in that object, it gives you true or array. isNA with this assign, this is also a function. So the way you run this function is you just put in the right side a number. If I do that, then I get position number 2 to be missing. So it implement that missing to the position that you identify here. You can identify as many as position you want as an array, and you get the missing in your vector. So as you see here, when I say isNA and assign 2 to it, it's replace 2nd item to be NA. So this is also another generic function, this suitability. In R, most of functions, by function I mean a procedure that you apply to a value and you get a result, right? So in R is not like exactly one variable function, you can get multiple outcomes. So, but I think you should be able to, you should know the basic R, as we posted in introducing the workshop. So I'm not going to go over every detail, but when is necessary, I will talk about that. And also you can ask questions about those codes in the chat. When I do mean X, most of the function, as I said in R, do not ignore the NA and gives you NA as a result. So basically it fails to run mean based on observed values. mean, sum, and a lot of other function has. So basically, you need to define what you want to do with the NA. So if you look at, for example, help of the mean function, you can see there is an option for NA, which is NA remove equal to false. Then you can define that as true. So then NA will be removed from this computation. So if I want to get the mean of available cases, mean available observation element of the vector X, I can just run mean X, NA remove equal to true, and that gives me some of this observed value, right? Oh, mean of this observed value, sorry. Mean of 1, 3, and 5. And if I run sum, then I get 9. So as you see, sum is 1 plus 3 plus 5 is 9. And the mean, ignore those NAs and divide it by, it doesn't divide by 5, it divides by 3, number of available cases. So now we ran the first basic analysis with missing data. Let's look at drawing a random sample in R. So in R, we can draw a random sample using from some distribution, mostly using R and the distribution mean. I talk about that because I want to get you to get the idea that when we want to impute missing data, we draw a sample from some distribution. And we will talk about that later. So for example, here, I set the seed because I want every one of us, when we run this code, get the same result. So if you don't set the seed every time you run, or different people run different code, or based on their computer and some specific, start from a random generating a string of values and gives you different random number. So if you run this over and over without setting, you get different value for this y1. Y1 has length 25. I didn't put the mean and the standard deviation, but by default, mean is 0 and the standard deviation is 1. A standard deviation of this normal population, normal distribution that I want to generate data from. So if I set mean equal to 1, a standard deviation 5, then I can generate 25 random variable from this distribution. I can draw a uniform random sample, which every value has the same probability from value 0 to 1. I can draw this R uniform, this Z vector of size 25 with the between 0 and 1. So the value outcome never can be less than 0 or bigger than 1. Here, what I did, I replaced some of the value of y, this y1, random variable, normal random variable, condition on z. So if z is less than some value, then I create a missing to this vector y. So if you run this, then you get some missing in the variable y. So now as exercise, we draw a standard normal vector of size 25. And for each value greater than 1 and less than -1, we replace y2 with a missing value. So, and then we can put them together to create a data set with missing. So let me go to R and try this exercise. So this is the code that you can get from, and you can run if you like along the workshop. So basically, this is the code that I ran there in the slides. I get the sum NA, but I have to remove the NA. I have to tell the function to do the computation based on only available cases. So if you run this, you get the y1. If you want to see the result of y1, you can just type y1 in the console. So you get all these values that generated from a normal distribution. By the way, in R, you can save your code as a source code. To do that, you go to File, open a new, you can open an R script and type your code and save. Like I saved it here as codes.r. And you can also, if you want to run a code here, you can put the cursor anywhere in this. Don't select partially like this data. You have to select either all of it, or you can click on somewhere and then Control Enter will run. Or you can put it there and just run.
Kivash, we can't see your R.
Oh, sorry. Let me share. Do you see it now?
Yes.
Yes?
Yes.
Okay, sorry about that. So again, this is the R code that I posted in the workshop page. You can basically download this code and run it into R, or you can copy paste it from there and then create a source and then paste it here and run it along the workshop. Or you can copy each line in the slides into your R and run it to see the result. So basically, I ran these codes and I was explaining if you want to run the R code from the source, you can just click anywhere and click Control Enter, or you can run it from here and get the result. Or you can type it in the console or copy paste it in the console. So paste, and then you don't see nothing because you didn't print the result. So you can do this, or you can type A and enter, and then you can see the result of that object. So here I created a vector of size 5 with 1 NA. And then I test is NA, which is true at 4th place. And then I get which place is NA. I did the sum to get the number of NAs. Remember, this is not sum of X, right? This is NA, doesn't have any missing. Is a logical vector of true and false. So if you want to part of the code only ran, you can just do this. You can select that part and Control Enter to, or Command return in the Apple computer. Here I included another missing. So you see there is another NA at position number 2. You could do several points. So I could add like C1, 2 and create position 1 and 2 to be missing. I'm not gonna run it. So if you want to run some function in R, most of them you need to identify what the function needs to do with them. So this code doesn't give you the correct answer, it just gives you an A. But if you identify the way you want to handle the missing, which is here, is removing missing value from the data. You can set seed and create this R norm. And here I create another variable y2. And then I created another variable z1. And now condition on Z1, I created some missing in the variable. When I say variable, it's just a vector of numbers. Basically, it's a sample from normal distribution. So when I run this, then if you type, let's type Y1 in the console, and you see that the NA that is created here. Okay. So this exercise asks you to create a draw a uniform. Then I draw an R node. So let's say uniform. Actually, I meant here by, let me go to workshop. I think I changed this. Normal, and then less than, bigger than -1, and then create a missing. So basically, let's do this workshop, this exercise. So I want to draw a normal, a standard, draw a standard normal random vector of size 25, and for value greater than -1, greater than 1, and less than -1, I want to create the missing. Every time I put the number sign here, that line doesn't run. So basically, I need to create this uniform. So I'm going to use, actually, this Z is R norm 25, and you can identify mu is 0 and standard deviation is, but by default is 0. So I created this Z2, and then I replace Y2 with a missing value. Actually, that's what I want. But anyways, then I can replace Y2 when Z2 is bigger than 1 or is less than 1, right? It cannot be bigger and, right? So you have to put 4. So if I run this, then I get Y2 with some missing. And then if I put them together, I get the data set with some missing. If you want to see this data, here also you can just click on this Y, and then you can see Y1 and Y2. I didn't change the name. I think I did. Oh, that is basically my data. So you see Y1 and Y2 has the value that was exist there before, but this NA caused by that variable Z, right? And then you can create another data which has the same size and of that data, which identify where there is missing. So if you say not is NA, that means if it's NA, then you get true or false. So is NA gives you true if there is NA. Not is NA gives you false if there is NA, and true if there is observation. So I do this, and then I create this as a numeric variable or numeric matrix of 0 and 1. And we call these missing indicators. So let's go back to our slides. So here I created those missing, and then I did this indicator. I changed the name of R as R1 and R2, and then I put them together. So now I have this Y1 and Y2 with R1 and R2, which I just showed the first 6 number of them, first 6 row of them. Now, this R1 and R2 shows 1 when there is observed and 0 when there is missing. So here, Y1, R1 is respected to Y1. So if Y1 at position number 2 is missing, then you have missing here. So let's talk about missing data mechanism. Basically, what we did was somehow implementing missing data in a certain way, right? Basically, missing data mechanism is a process that generates that missing data for you. Missing data mechanism generally fall into one of the 3 main categories: missing completely at random, missing at random, missing not at random. And those are very important to understand when you want to deal with missing data. So let's define them. A variable is missing completely at random if neither the variable in the data set nor the unobserved value of the variable itself predict whether a value will be missing. So what it means? So it means this missingness or this missing indicator is not depends on the value of Y1 itself that causes the missing or any other variable in the data set. That is missing completely at random. We will talk about that more in short. This is the strongest assumption that you can make about the missing mechanism. By strongest assumption means there are very few methods that you're allowed to run a few methods by using this assumption. Remember that in regression model, we assume, for example, normality for OLS. This is something that like that. OLS is valid when you can assume something, right? Equality of covariance, things like that, or normality. So this missing completely at random is the strongest assumption. So when data missing completely at random, analyzing only on the complete cases is unbiased. So if you drop the cases with missing, then your result will be unbiased. So you need that assumption to get the unbiased estimate if you drop the cases. And we will talk about more in the drop the cases, which we call also leastwise deletion. A variable is said to be missing at random if other variable, not the variable itself, not the value of the missing that causes that missingness in the data set. For example, in a survey, men are more likely to decline answer some question, for example, about their job or about their age or something. So that missingness caused by other variable in the data. So basically, in that case is missing at random. This assumption is more liberal than missing completely at random. So you relax a little bit of assumption of missing completely at random, and we call that missing at random, which the name itself sometimes is confusing because you think it's missing at random, but no, basically missing is dependent on other variables in the data. Multiple imputation and other random modern methods such as maximum likelihood generally assume the data to be missing at random. A variable said to be missing not at random if the value of unobserved variable itself predict missingness. So if that value is very large, then you won't observe or is going to be missing. Or if it's very small or in certain range, you have missing. So for example, income is a good example of this type of missingness, because maybe some people with high incomes more likely to decline answer about their income, or people with very low income maybe decline to answer about their income, about the variable itself. This assumption is the most liberal assumption, and is very hard to deal with that because there are probably not many methods or not at all method exist to handle this. And any other method, you will get some bias. So now we talk about the variable. If all variable in the data set are missing completely at random, then that data set is missing completely at random. If at least one of them is missing at random, maybe, or some of them are missing at random, others are missing not at random, then that data set is missing at random. If at least only one variable in the data set that you need to use in the analysis is missing not at random, that data set is missing not at random. So look at this figure. In this figure, X and Y are, X is, think about X as all observed for now, and Y is the variable with the missing. So in the data set, you want to find the relationship between X and Y, and assume there is some correlation between X and Y. R is indicator vector of Y. So you can see also Y as a set of random variable, but for now, just think about that as one random variable. So R is 0 when Y is missing. R is 1 when Y is observed. Z is some other cause that missingness related to that cause, and that Z is not observed. So in this case, you have missing completely at random because the missingness doesn't depend on any variable in the data. Now, in this case, not only Z might cause R to be missing, there might be some relationship between X and the missingness of Y. In that case, you have missing at random. So missingness is not independent to all other variables in the data. In this third case, this missingness directly might be related to the value of Y itself. So R and Y are not independent. In that case, you have missing not at random. And this graph comes from the book of missing data mechanism, missing data by Schaeffer and Graham. There are a lot of talk and discussion about missing data mechanism and how to handle a specific situation when you have panel data or data like that, repeated measure data, things like that, and then you can find it in these books and references. Any questions so far? If you want to ask question, you can unmute yourself and ask. Otherwise, sure.
Is there any threshold for missing values to be accepted?
You mean
Or how?
percentage?
Yeah,
Percentage of
proportion.
missing?
Yeah. First question is a proportion. Is there any like threshold rules of thumb for like missing values? And second is there any? How can I determine this data is missing completely at random or missing at random? Is there any statistical test to
Very
perform?
difficult. Yes, yes, good question. Today, there is not a definite answer. For some specific questions, what they do, they look at the missing pattern and they compare their mean and covariance metrics. But still, those tests are not robust. So they are in very specific case, you can run those, but they are not definite. So the best way to identify that is understanding your data and do you think you can make that assumption? And other thing is doing sensitivity analysis. So those are the things that can kind of identify. So sensitivity analysis, I mean that run the methods that can handle missing completely at random, and the method can handle missing at random. Then if the result is not much different, then we can say, oh, probably is missing completely at random. But if the result is dramatically changed, then for sure you don't have missing completely at random. But today there is ongoing research and is not very definite to identify whether or not the data is missing not at random. About the percentage, hopefully if you have less missingness is better. But you cannot do, as the percentage of missingness increases, if the assumption are not valid and you make those strong assumptions, you get more bias. For example, if you're running a method that can handle missing completely at random, and then there is a little bit of missing at random, then probably you don't see much of the biasness. But if you have larger percentage of missing, then you will see more biasness. So those are related. There is not a specific threshold. There are some simulation have been done, and in Craig and theirs suggest that even with about 40% of data missing, and if you have missing at random, then multiple imputation gives you a good result. Good result, again, remember we talked about using all the information. Of course, we don't have all the information, right? We have missing, but we can retain variation very well. So yeah, and then the result will be unbiased. Did I answer your question?
Yeah, thank you. Thanks a lot.
Sure.
Thank you very much, actually.
Sure. Less missing is better, always. And always, if you have some other information based on your expertise on the analysis that you're running, that is very much preferred and is very helpful. So in this example, next example, I'm running a multivariate normal with some sigma. This sigma gives me the covariance matrix, basically variance of each variable I want to generate a bivariate normal, and I want the covariance between those two random variables to be 0.5. Basically, I try to generate a missing at random data. So in order to do that, there is a multivariate normal function in the package mass. If you want to run a specific function from a package, you can use colon. And this understand this function, it is in package mass. So if this function exists in other packages with the same name, it doesn't get confused. So I generate 100 sample by variate normal with the mean of two variable 0, and then I create a diagonal of 2 gives me a identity matrix 1 1 in the diagonal and 0 off diagonal. So when I multiply by 0.5, the diagonal is going to be 0.5. Then I add 0.5 to all the elements. I get. How about I show you that? Do you see my R? Yes.
Yes.
Okay. So basically, this diagonal 2 gives you this identity matrix. So every matrix times this is going to be that matrix itself, basically, if the dimension agree with each other. When I multiply by 5, I get 0.5, 0.5 here, 0, 0. And then when I add 5, I get a covariance matrix of diagonal, which is variance, and off diagonal, which is covariance between these two variables, to be equal to 5. So they are related, right? So there is like linear regression between these two variables. And if I run this, if I run this, oh, it shows that. I get that y as multivariate normal. And then I want to generate some missing data there. So I say, if a y1, if the first variable is less than -5, then create this R1, create this basically indicator for first one. Actually, yes. So I create this indicator, but this indicator is for the second one. So I said, if this is less than 1, create R1. I think I should do this. R1, yeah. And then it doesn't matter, but I should do this R2, R1, and then put this R1 and this R2, but it's the same result. It's just, so basically I create this R1 to implement to Y2. So I want to replace Y2 when this R1 is less than 0.5. So if I ran this and ran this, I get this R1 and R2 as missingness. So again, this is true and false. I can use that true and false. If it's true, then I replace it to NA. And then I can create this data, which is missing at random. So if you run this, look at this head. So this value is missing. And the cause of this missingness is this value. And since there is a relationship between this Y1 and Y2, this data is missing at random. Make sense?
Yes.
Yeah, okay. So Another method to deal with the missing data is, which is very popular, but I tell you this is very wrong, is imputing the data with the mean. So let me go back to the slides. So now we are going to talk about the methods that we deal with the missing data. There is a paper that say, okay, the best way to handle missing data is not to have them. Of course, if you have all the data, again, missing data is a challenge, right? So it's not good information, but if you have missing data and it's at random and you know cause of missing, you can recover that missingness by some statistical method. First way is to just drop the cases with missing, which we talk about that. So basically every case that has at least one missing, we just drop that in the analysis. This is called listwise deletion. And again, we said that if the missing data is completely at random, this works. But the problem also with this is that you might end up with not having any cases with complete data. So basically you start with a sample of 100 and then you just delete all the cases if you have many variables. So then you end up with like 10 cases. So that's not ideal, right? Mean imputation. So how about we impute each variable, but by the mean of that variable? Again, this is okay, gives you unbiased estimate if you have missing completely at random, but it doesn't give you a precise estimate of uncertainty. So in here, I use that data, DAT, and I calculate mean of each column. Basically, I run a loop going from column by column, calculate the mean, and then impute the missing by the mean value of that variable, right? This is the specific NA remove, drop the NAs, calculate the mean of available cases for that variable, replace the missing. Is it missing true? Then it replace that with that mean value. And if I run over all these values, you know, I can do mean imputation. Later, when we talk about mice, we can see easily we can use mice to do that for you. Okay. But again, this is not ideal. Mice can do better. So if I do that and I do apply mean and standard deviation, right. So the question is, what is the problem? Let's talk about if I have missing completely at random. Does those mean value of y1 and y2 by imputing the missing with the mean changes? If I have, for example, 100 people, and then I calculate the mean of 50, and then let's say 50 of them are missing, and then impute the mean. When I get the mean of everything, does the mean changes compared to when I calculate the mean only for available cases? Yes, no? So here I calculate the mean of only available cases. As you see, the mean doesn't change. It's the same thing, right? Because we just impute the mean and then we average. So if you average 100, you get 100, right? So it doesn't change the mean. But look at the standard deviation. The standard deviation changes. This one doesn't have a missing, so it doesn't change, but this one has missing, and the standard deviation drop, right? So you don't recreate the standard deviation correctly. This case was missing completely at random. So another better method when you have missing at random is to use predicted value and just use that predicted value of the other if there is the relationship between these two random variables and impute based on that predicted value. So here is one example. Let's say we have IQ and job performance, and we have IQ of job performance of these people, but we don't have job performance of these values, these IQs, right? We can run a regression model using the available cases and then get the predicted value of job performance given IQ. Then we can impute the data using that. This is better than if you just use the mean of all the job performance, because as you see, somebody with higher IQ has a better job performance, right? So you implement that relationship in the imputation. But as you see, you don't implement uncertainty, right? If the real world, if you didn't have missing, you should get some uncertainty or variation, right? This is called single deterministic imputation. If we want to do a little better, we can include some uncertainty. So in order to do that, we can get this predictor, but you can sample from error or residuals for existing point or complete cases. And by randomly sample with replacement, you can just add those variation to this data so you get some better kind of mimicking the reality, right? This is good. Still, there is some problems, but when is missing at random, you can do this stochastic imputation, right? Single stochastic imputation. So we get a single imputation. Now we have complete data. We run the analysis and we call the data. Okay. But the problem is those predicted value used the existed data, estimated the coefficient of those regression models. Those are not real parameter of the population. Those are not actual relationship. We estimated that using that. So there is uncertainty on that estimate, right? So we want to get that uncertainty included into our imputation. Another method is full information maximum likelihood. Full information maximum likelihood is a way to get around the missing data. Basically, as you know, that maximum likelihood calculated likelihood of all the data together. Full information maximum likelihood calculate case by case likelihood function and maximize that. So there are a lot of computation involved, but full information maximum likelihood in some cases, some analysis gives you a very good result. Kind of iteratively imputed the missing data, but beyond, underneath, you don't see, but it's iterate to get the last imputation. So it's not exactly multiple imputation, but it's very close. And then multiple imputation. And I will discuss that multiple imputation in next slide. So this is not multiple imputation. This is single imputation, but we include the randomness. The problem again with this is that this predicted value depends on the data. Okay, depends on the estimated predictors that estimated from these available cases. Let's stop here a little bit. Any question?
I have a question.
Sure, go ahead.
For your single imputation above in the graph.
Mhm.
So the idea is that you're extrapolating below 100, and you're assuming that the distribution is a little bit the same from the right and the left, and that's the problem. But if your missing values were within the minimum and maximum, so within 100 and 140, so the missing values within there, would that be more or not? Not
Probably,
really.
but remember, look at this. There is no variation here, right? So this is kind of like mean imputation in 1 degree better, because you use another variable to use that mean imputation. Remember, predicted value is a mean, is average, is a predicted of y given x.
Right, but then adding that variability within that range in addition to that, right? But I understand. Okay,
Yeah,
thank you. Yeah.
Sure. Yeah, I see what you're saying. There is 2 problems here, right? There is one that we don't know that relationship exists here. That's perfectly very good point. Very good point. However, if we didn't have that problem, still we had that problem of recreating uncertainty. So yes, exactly. This one, it tries to add some uncertainty, but not completely. It still is single imputation. What if the data give me different slope and different intercept, right? Those uncertainty is not here. So there are ways to deal with that, and we will talk about that. The multiple imputation basically tries to do that. Basically, what it does is 3 steps. Instead of imputed once, it impute many times, right? So basically, you have a data with missing. You impute it many times randomly. So every this imputation has some uncertainty. You can include that uncertainty by creating uncertainty in the parameter itself. So basically, one good idea is think about the regression model. Regression model gives you a coefficient, and it gives you a standard deviation of that estimate. Now, if I think about that coefficient estimated as a normal distribution, right? And I draw one sample from that parameter, from distribution of that parameter, estimated that parameter. Remember, in frequency statistic, we say parameter is unknown, we don't know, is fixed. Parameter is beta, but beta hat is the value we get from the sample. And then when we get beta hat in the regression model, you have a standard error, which is what is the standard? If you take another sample and another sample and another sample, this beta hat will be different every time. So it tries to estimate variance or a standard error of that statistic, right? Or that function of the data, right? So if you draw a sample from there and then impute, and then do that again and do that again, you're better, right? Then you include another level of uncertainty. And then you analyze your model, whatever model you have, logistic regression, and you get the result. And then the next step is how you combine this M imputed imputed result, imputed data, imputed result, and they combine them together to get a single result. And then how you can combine standard errors to get the standard error of this combined result. And that's basically what the multiple imputation does. So it gives you a better estimate of that variation of those results, basically. Right? This is general for any type of multiple imputation. Now, there are different methods. So in some method, they do imputed data differently. So the difference always is here. When you want to impute the data, the analyzing is the same. And the combining basically is, there are probably many, but there are one kind of a standard. There are very standard method to combine this result. And they are mathematically sound. But the way you impute is important. How we impute to include the uncertainty. Right? Now, I haven't talked about type of variable, right? Normal, binomial, whatever it is. Think about a way to get the predicted value, just like that. For simplicity, for now, think about all the variables are continuous and has normal distribution, or some sort of continuous distribution, right? Okay. So in here, I explained some different method of doing that part imputation, and some different packages use different method to do imputation. So one very popular package, Amelia package, that what it does is every time wants to estimate those parameters, it takes a bootstrap sample from the data and then run a regression model to predict the outcome, the imputed value. So every time use a bootstrap. So that way it implements the variation to those parameters to kind of mimic the population variation, okay? So briefly, I explained it here, but I'm not going over that. It's beyond of the, not the scope of this class, but it's a lot. But this one is the method that MICE is using. It's fully conditional specification. Basically, they use some sort of chain equation using Bayesian and MCMC to apply those uncertainty of the parameter that you want to impute or predict every time. Make sense? So basically, as simple as that. So if we go back here, right, this is adding variation, but we use this fixed one time. Now, the Bayesian type of way is using a prior, randomly sample from the prior, implement the data, get a posterior, but it has to go one variable by one variable as a chain of equation. And that allows us to implement different method of prediction. So you don't have to start with the linear and normal. You can predict using binomial if you have binomial outcome. You can predict using multinomial. You can predict using ordinal. And there are lots of different methods that you can use to do the prediction. And there is a lot of method to implement uncertainty that might be there and we didn't see, right? So that's the advantage of MICE. And here explain which one is easy. Bootstrap is faster, but this Amelia package assume that the data is no multivariate normal. So, and then I talk about the expected maximization. Basically, this is like an engine of creating those, how to estimate. You have missing data, how to estimate those parameters. And it goes through EM algorithm. I'm not gonna talk about that, but it tells you iterative method. So basically the reason I said it's kind of like multiple imputation is that. So iteratively generate those to get to the stationary or, you know, a stable estimate for the parameter. But let's skip this one. And then we are going to, let me continue a little bit, and then we take a break to go back to continuing mice. Any questions so far? Any question? Yes.
It's still kind of, but if you don't know how to, if you don't know the data is missing a completely random or something, there's a pattern behind. How
Right.
do you decide the algorithms, what you just mentioned? Do you just do by your guts, or is there any rules of thumbs, or?
Okay, so let me answer you this way. If you don't think that missingness is because that value was so high or low, that is easier to kind of understand. If that's not the case, missing at random is good enough assumption to use multiple imputation. So again, missing at random is stronger than the missing completely at random is stronger than missing at random. Missing at random is a little liberal compared to missing completely at random. So at least we can handle missing at random. Now, if the data is missing completely at random, and this missing completely at random is very strong, and percentage of missingness is very high, we have to be careful. Or we can drop that particular variable that changed the analysis a lot from the analysis. So there are methods to do sensitivity analysis to investigate that, but to be honest, it's not easy. Without outside information, without any information from your data, based on your expertise. If I look at the data and the missing is, because the missing not at random, you don't even see the cause of missingness. You don't see the value, right? How you know that missing is because that value was high. There are methods. For example, using auxiliary variables, using other variables that somehow can predict this one, but it's not, you can find it somewhere else. If you have those variables, that is helpful. So one way is using auxiliary variable. The variables are not, you're not using in your analysis, but can somehow predict that missingness. So, yeah.
Sorry for coming back then.
Yes, sure.
Sometimes I kind of read that the missingness also contains the information. Then do you recommend with the missingness to do additional analysis and then separate the data set and then do further analysis on the two different data sets? One has missing values, one doesn't have the missing values by variables.
You mean like one with listwise deletion, one with the missing address? Yeah.
Yes. If I
Yes.
say so.
that will tell you that the data is missing completely at random or missing at random, right? But it doesn't tell you about missing not at random. So again, but you can, if you have some information, outside information that can somehow tells you something about the sample that you collected, that might be useful. So there are many methods, and this is again, it's ongoing research. But you know, this is we try to do our best. So if with less assumption we can get a good result, then we should go that way. Also, in multiple imputation, there are many different methods to do imputation, and those need to be investigated to see if the other different method gives you a better result or different result, and that might give you some insight. Okay. Again, in the package mice, there are documentation about the sensitivity analysis that I'm not very familiar with. So I will, I like to get to that at some point. Okay.
Thank you. Thanks a lot.
Sure. So, okay. Years ago, I had a package in R to test for missing mechanism and published in a very, in a psychometric journal, which is very popular journal in psychometry. But I don't believe that in some specific cases works, but you know, is very is not robust test. It means that if you run the test and if you run the test in another different type of the data with a specific kind of relationship or a specific type of missingness, it might not work. Or different sample size. Sample size is very important in those analyses because again, we are using different pattern and sample of each pattern is very small. So those kind of tests are not, and those are tests of missing completely at random. So, yeah.
I have a quick question.
Sure.
So we're dealing with a lot of these like NA values, but are we also including in R they have this NaN value? Are we encompassing that as well, or is there a distinction?
Yeah, this those values are not particularly missing data. So you need to make, you know, you need to investigate what caused that NaN. So if you divide something by 0, you cause that you get the NaN, then that doesn't mean that is NA. There is some information. There is a percentage that you wanted to calculate, and that percentage might be very high. So it doesn't make sense so you have some information, some prior information. And that's you need to distinguish that. So yes, but yeah, you can replace it with NA, but NaN is not missing. Right? So that's another thing that it was a good question. Thank you.
Thank you.
Sure. So let's continue in this. So let's talk about mice. Mice, again, do that 3 phase of dealing with missing imputation, basically. You have incomplete data, which is a data frame. And then there is a function is mice. These are the most important functions in the mice. Mice width, and pool. So what mice does, it takes incomplete data, and based on some argument that you input here by, for example, telling what type of imputation, what variable impute what variable, things like that, you basically get a set of imputed data set. And the result of this mice is an object. Again, R is object-oriented package, right? So you have everything in R, every variable, let's say, is an object, right? A plot is an object. A table is an object. A data table is object. Data frame is object. Array is object. List, vector. These are different objects. And is object-oriented because every time you run a function, you look at that object and you understand how to implement that function to that object, right? So if you include data frame, mice understand this is a data frame. It needs that data frame as input, and it gives as a result an object of class MIDS, multiple imputed data set, right? It holds some information that from that information you can get imputed data, each of imputed data. Is not a data frame, is an object MIDS. And then function width takes that, and based on the analysis that you define inside this width, gives you the result of each multiple imputed data, and it calls multiple imputed I don't know, regression analysis or results analysis or something like that. So it gives you an object of the class Mira. So you get the data frame, you use mice, you get the meets, you use width, you get the Mira, and then pool gets Mira and gives you MePool, right? So it gives you multiple imputation pooled result, which again has some more information. It's not just one result, there is more to it, right? So that's why they have to. That's a good thing about R, that you can define a specific class to store the result, the information. However, if you have multiple data already imputed from, let's say, SAS, you can read those in R, and then with bits, you can combine it and then pull it. You don't have to do this step in R. So that's another thing. We are not going to discuss that, but that's another advantage of using mice. So it's very friendly with other results from other softwares. So it gives you a very flexible way. It gives you impute the data in a way that is more realistic. So if you have a categorical variable, let's say low and medium and high as ordinal, you can run some sort of ordinal regression model to impute that. So it doesn't give you, for a categorical variable, a numerical result. So that's good. You don't have to do it, dummy coded or things like that. So yes, absolutely. I'm going to edit a little bit of recording and we'll send it in a few weeks to the YouTube channel that Andy sent earlier. So with that, let's start. It's 2:37. Okay. So For this workshop, I'm going to use this old data set from previously we were IDRI. From IDRI website, now is WARC website, which is a data from high school and beyond, which implemented some missing data to it, and that missingness was missing at random for practice. So remember, this is not real data, it's just to illustrate the workshop. This data contains some demographic and performance of some high school, 200 high school students. And we want to, let's say, the analysis of interest is to run a regression model with some read versus, for example, write and math. And later we can add other variables for as predictors. You can run this code to get the data in your R. This is the address that is in the site, is in that page. You can either download it or directly run this code and get the summary of the data. As you can see in the summary, some variables are characters, some variables are numerical. ID, we don't care. There is a like numerical race. But remember, when we do multiple imputation, we want to include the variables that are in our data analysis. We want to include those variables in the multiple imputation process. And that is the consistency of the multiple imputation method with the analysis. So to retain the relationship in the data, in the analysis, in the imputed value too. So you see some of them has NA, and this prog and female doesn't have NA. Or when there is a factor variable, doesn't log character. So make sure to change all the character variable to factor. Okay, that is very important. Also, you will see it here. When I use that program, this is a program that they will apply for. If you make it as a factor and then change the reference group to vocational, so this has 3 levels: vocational, academic, and here it is, general. After I did that, then there is NAs. And that NAs, because by default, when you do factor, when you change the variable to a factor, there is something about missingness. It says exclude NA equal to true by default. And so excludes the NA and keep it as NA. So, and it doesn't keep it as one level of the factor, but you could also. That's different story, right? That's not NA if you use that NA as one level, right? So now you will see that prog has like 18 missing here and female has 18, and the other variable also are continuous. Social science status also doesn't have, is continuous, so you don't have to make it as a factor. You could, if you wanted to, as an ordinal. So it has value 1, 2, and 3. But we can also usually use a ordinal random variable as a continuous. But you can change it to ordinal and impute it if it had missing. So if you run a len function for example, let's say our analysis is read using write and math as predictors. By default, it runs it's drop the MX. It's not like it gives you the answer, but default of this function, different than the mean function that we saw before, is dropping all the cases that has either read, write, or math missing. And we call this model M complete, so complete cases. And after we run it, we get the summary. And in summary, if you look at the result, first of all, look at the degrees of freedom. Degrees of freedom is sample size minus number of parameters. So is 158. So how many sample size used for this model? How many parameter? 1, 2, 3. So it's going to be 161. So another way to get that complete number of complete sample size is to use this sum of complete cases. Complete cases of, again, we only use read, write, and math, right? If we use only these variables, then number of complete cases, again, this gives you the whether or not is complete case, and if you sum, you get 161, which is same as this value. So you get some estimate, of course. You get some slope here, a standard error. If the data was missing completely at random, then should we were worried about this estimate? Not really. Those estimate is unbiased. We are losing some information, right? We are losing some information. By losing some information, your confidence interval is going to be wider. Your standard error is going to be, even if the data is missing completely at random. Your standard error might not retain the standard error if you use all the available cases. But there is not biasness in the estimate if you can assume missing completely at random. So this is the first try, right? It deals with the missing data, right? Now, if I do mean imputation, I use the same method to impute mean of each variable for itself and run the analysis. And if the data was missing completely at random, this estimate, yes or no, would I get the unbiased estimate or no? Can you think about that? So remember, we had some relationship between these random variables, right? So by including only the mean for the imputed value, you don't implement that relationship. So then you might see biasness here. Maybe it's not great, but we will see bias. Also, the standard error is not going to get you don't get the good standard error here, because the percentage of the missing was low, was about let's say 40 out of 200, about 20%. The estimates are close, but the standard error for mean imputed is less than the standard error when you use the complete cases, right? Because you impute the mean value there multiple times, right? So that's the issue with the mean imputed value. Now, I'm going to talk about another way to get around the LN and run the linear model using full information maximum likelihood. There is a package in R called Lavan. You can run the same model. In Lavan, the full information maximum likelihood is implemented. So you can run a regression model. This is basically for factor analysis and same model when you have a latent variable, but also you can run it as a linear model using that same model. It's different language, different kind of universe, but is basically the same model. It's running the same linear model. Here I ran this using Lavan, using SIM, and this is the way you run a linear model. Basically, you define the linear relationship between observed variables. So there is no factor, so we don't define the factor. And then you have the data, and then you call missing is full information maximum likelihood. You could also use maximum likelihood, which is running in the same way. So I compare, I thought this is EM and this is full information, but the result is the same. And when I ran this, the result is here. These are the relationship between the outcome and those estimates. So these are coefficients. And this is the standard error of those coefficients. As you see, it uses Z value over there. You have the T value. It's not much different. But it's the same, actually, Z value, T value, I think is the same, but they use the Z distribution to calculate this P value here, not T distribution. And then you have this also a slope. Yeah, I'm sorry, intercept. So if you compare this to the result here above, actually, you know, what I'm going to do is I'm going to keep this result and then bring R. Do you see my R over the slide?
Yes.
Okay. So I read the data again. You can run all these codes here. And then you run the complete cases, and then you run the mean imputed value, and then you can get this table result. And then I can run the Lavan summary. It takes time, you see, it goes through iteration. See, it's a slope. It's not directly like OLS. OLS is very simple. It's just use the inverse of the function. So now you can see these two together. So you see this estimate of the slope is something between these two. The standard error is less than both of these two cases. For the slope also, this is very small, right? Because it's using mean imputed value, so you lose uncertainty. This is high because you don't use enough data set. So a standard error, you see there is a divided by a square root of n somewhere. Here is so you lose that when you have a smaller sample size. So yeah, pretty much you can see the result is different, but this use all the information, right? So it says number of observations 200, right? And then there is a loss of parameter is estimating and things like that. So don't worry about this, right? Because it's estimate also mean of each of those variable and variance of those variables. things like that. So that was Laban. So this is another way, is if it's available for that specific analysis, is good, but I don't know, like Laban can handle polar or different type of regression model. Not necessarily, and I'm not sure how they handle that. And as you saw, is slow too. So before going to mice directly, let's look at some of the nice feature of mice and also other packages that you can visualize missing data. This is very recommended, very much I recommend to look at the missing data pattern. Look at the percentage of missingness. Get the idea of what is missing, where is missing, and things like that. If your data has many variables, break them down to a smaller groups and investigate. This is important to see how the missing data is. So this nice missing data pattern from package mice gives you a nice idea about what variable is missing, what variable is not missing, and how many complete cases, all complete cases you have here, for if you want to use all of them. So remember, this is not only read, match, and write. As you add variable to your analysis, the number of complete cases decreases because it creates another type of, for example, female is here, and there is 15 cases like that. And there's 14 cases that program, and there's one, both of them are missing. There is science is missing there, 13. So you get a good idea about how the structure of missing is there. So again, going back to the test you asked, what it does, it looks at all these different patterns. One method by Little is very popular. It tests whether or not the mean of each pattern multivariate mean comparison are equal. That's one test. And there is another different type of test. It's compared with mean and variance equality and things like that. So, and it gives you the data pattern. You see, this is the indicator. This is only unique of each pattern missing indicator. So this is all observed. And yeah, this is 0 and things like that. Yeah. And then it tells you like 1 missing. And in this pattern, there is 1 missing. Most of the pattern, there is only 2 missing, right? So you get this good idea about your data. So in some, again, as I said here, in some data sets, because there is a lot, but there is tons of different packages can visualize your missing data. So is a good option to look at it. Sometimes you either want to include in your publication. There is another package, VIM, that gives you this also nice plot of the missing pattern and the percentage or proportion of missingness for each of the variables that are missing. And then it gives you that portion of missing for each variable. Again, overall was about 20%, but for example, program has only 10% missing about. There is another one, it calls margin plot. So this one is nice because this one tells you that the missingness depends on other variable or not. So you can look at pair of this variable. For example, here I look at the math and read, and then you can see this 15 is 15 math that are missing, right? And the read value for these 15 math missing are very much the same, has the same distribution of the other non-missing read. So for this one, if I had a very all of them here or here or here, right? Then I could say, oh, you have missing when the read is high, you have more match missing. So they are related. So this is like a spread, so there is not really much relation. This is kind of things that you need to think about testing. So as I said, there is no established good test to test missing completely at random and at random, but there is heuristic way to look at these kind of plots, which this one is very interesting to look at that missing data pattern. You can run this over the data that is imputed to, but I didn't include it here. In mice, you can do different method of imputation, right? So you can do mean imputed. So before going to the default method and more complicated, let's look at the simple. So mean imputation, m equal 1 is one imputation. And because it's mean imputation, there is not a number of iteration, number of chain that you want to use to impute the data. So that also is, in this case, is important. We will talk about this later. Okay, this number of chain, this number of imputation. So basically, this gives me one imputation using the mean of each variable to impute the data. And as you see, if you just run this and look at the imp, which is the class of meets missing imputed data set, this is the class that I was talking, right? So you give the data frame, you get a meets, right? So one imputation, no iteration. Now let's talk about what is that iteration. That iteration is the chain. So again, we wanted to retain the uncertainty of the parameter estimate. So when we have, for example, 10 iteration, for each imputation, mice start from a starting random from prior distribution, implement data, get their posterior, use that as another iteration, and go to the chain. So each one chain means one time going from first variable to the last variable, impute first the first variable, then the second variable, then, and one whole round of imputation of all these variables is one chain. And then next time use the last imputed value as the beginning point, and then it's imputed one more time. So basically after impute, then it's used that as a data, and then random posterior as the prior this time, and does that until to get to a point that we call it a stationary point in MCMC. So what I explained basically was very simple way of, it's more than that, but it's MCMC. Basically, the goal is to draw a sample from the last imputation, the last iteration, draw a sample that pretty much gives you a good drawing from a population of that predicted value. That's what we wanted to do. So if you want to extract the imputed value, if you look at meets, there is you know, in the next slide I show you, there is different object there. This different is kind of a list of other objects, but you can use complete over this object meets to get the complete cases. So this is the data and this is complete. And as you see, the mean imputed for right. So this is imputed data set, but one data set, one single imputation. So As you see, the column means is this value, which is the value that imputed here, right? Column means gives you the mean of each column. And remember, because there is missing, so if you don't put that, you get NAs. Now, we can fit for that one single imputed value the method that we wanted to do. So this is basically a function or the analysis type. We can put it there. You can use that analysis in the one like function, or because this is a simple ln function, I can just type it here, right? And then I give the meets, and then I get the mira, right? Mira apply this ln to each complete case and gives me the summary, right? So because it was only one imputation, this mira is basically, this tells you what kind of classes is mira. Also is a matrix, as matrix of all the results. And you see, run the analysis, number of observation, one analysis on the imputed data, and it gives you this result imputed by me. Estimate, standard error, and statistics, which is estimate divided by this value, and then gives you the p-value. This is like a t statistics. Okay. Now, let's do this imputation using the regression imputation, one imputation again. So normal prediction is just multivariate normal prediction, which is same as OLS. So if we run that, we use that deterministic imputation using the relationship. But again, there is 3 random variables. We use 2 of them to impute the third one, and then in next time we use the other one, use the other 2 to impute this one, and then the whole thing is one chain. So if we want normal prediction, it gives you that. Based on corresponding value of other variable, then impute the missing value with the predicted value. There is no uncertainty that added to this. So this is another method, right? Still, none of them are default method. So again, this was one imputation. Missing stochastic imputation, the one that I showed you that we add the randomness, that's a stochastic imputation. So this one is kind of, I think is a better than just randomly sample from the error, but it's very similar. It's very similar method, but it adds that randomness. I think it draws the parameter from the distribution of the parameter estimated, and only one draw. So it gives you that standard error. Basically, you estimate the more accurately the variation. But again, this is only one imputation, right? And because it's a stochastic, if you run it one time, you run it the second time, you get different results, right? So there is an option to set the seed. So every time you run it, you get the same result. This is good for reproducibility. So if you want to publish, you need to have the seed. Let's say 5 years after that, you want to run the analysis again, and you see all the result is different. What happened? Because you didn't set the seed, right? So that is important in doing this kind of stochastic imputation, right? So I set the seed, as you see, this one is different than this one, a little bit, right? But it's another imputation, right? But still, this is, if I can, now I can change these two, I'm sorry, change this one to another number. So every imputation have different result. So I can do 2 imputation. Now let's look at the default. There is a nice thing about this default. It doesn't do those kind of stochastic. Basically, it use the method called for continuous variable. But by default of mice, look at type of the variable you have and use the one that is fit with that type of variable. If it's continuous, it use PMM. It calls predictive mean matching. And I'll tell you a little bit about that, but there is a lot more to this. And there is different type of predictive mean matching. And there is like a set, parameter that you can set for that. But again, mice is a huge package, and I don't think we have time to go over every detail. But you can look at the reference of mice. This seminar is for you to get comfortable and start your multiple imputation in your analysis. So if I don't define anything, the number of imputation by default is 5. The number of iteration also is 5. One thing in the quotation here, MCMC usually needs a lot of iteration to get to a stationary point. And what that means is, every time you sample in MCMC, your sample depends on the sample before, right? This MCMC, the beauty of that is because use the certain type of sampling, at some point, this Markov chain of randomly sampling is independent from previous sample. So it gets to a stationary. In mice, you don't have to run iteration like thousands of times. Usually Markov chain Monte Carlo needs like 10,000 iteration to get to the stationary. Mice gets to the point that each sample is very much independent from the sample before, because the method that it's implemented there, the way that it samples, and include a lot of uncertainty that overcome that dependency between each sample. That's what they say. But they did a sensitivity analysis, and they see like you don't need many iterations. So those iterations takes a lot of time and computation. So this makes it faster to impute. So here we did impute 5 times. You see impute 1, 2, 3, 4, 5. And then iteration 1, 2, 5. So it reports this for you. If you don't identify that, don't print the report, right? Don't print all of this. So you can specify that. So if you just type it, print that I impute that meets, you get some information, right? It tells you what type of method is used for each of those variables to get imputed. It gets the predictor matrix. So it tells you what variable is used to predict what variable. So by default, every variable predicts every other variable. So basically, read doesn't impute itself, right? That doesn't predict itself. So read use the regression of, let's think about regression. Math and write to impute read. Math use read and write to get imputed. Write use read and math. You can specify this after you're running a mice with one imputation, one iteration, and then change this value and then give it back to the mice. So for example, if you don't want write to predict read, you only want math, you can set this value to this predictor matrix, this value to 0. So then write doesn't predict read. So these are the flexibility that mice gives us. Very simple. And then you can define what type of imputation method you want for each of those variables, right? You can change one of them, for example, use normal for this one, because I feel that normal is better for this, right? So by default, it's predictive mean matching. Now, what that means in very vague definition. So it gives you a prediction, right? It doesn't impute using that prediction. It says, wait a minute, let's look at the closest existed predicted value or the values that is in the data. And let's say there are 5 values that are closest to this. And out of these 5 values, randomly select one and impute that one instead of using that predicted value. So basically match those existing value or match those, again, I said different way, that's what is. Each of these different way has a benefit, and there is a simulation they done to get the bias in different situations. Some of them is, and there is a lot of things they talk about that, and there is a lot of unknown, still they don't know. And they need, yes, as Andy said, again, yes, that's a good point. Now I get back to this. If in your analysis, for example, you have right a score, like right a square in the analysis. So let's say we want to analyze read is predicted by math and write a square, or read is predicted by math and write an interaction between write and math, right? You need to impute those also, and you need to use those to get the imputation. And there is a concept of passive imputation, which is also important to know, because sometimes you have a variable that transformation of other variable, for example, interaction, math times right. Math times right cannot be different if you impute math differently and write differently. You cannot impute it separately. You have to, these should be exactly the value of this multiple by each other, right? But however, in the imputation process, you want to impute other variable in the model using this interaction, because this interaction is in the model, right? But also you don't want to impute math and write using this multiplication, because this imputation comes from those original values. So mice has a way to get around that, and it calls passive imputation. We don't have much time to talk about that, but the thing that is important, you need to use every variable that you want to use in the model in the imputation process to get consistent result. That's called consistency. Yes. Let's look at the object meets in more detail. If I do attribute IMP object meets, right, you get a lots of information, right? Iteration, seed, chain variable, log event, chain mean, ignore, blah. There is a lot of things, but there is also this predictor matrix, and there is this method, which are very important. And the class, of course, is meets. You can get extract imputed value using this $ impute, because this was there, right? Impute, and then get the imputed, not the whole did not complete, the one that is imputed, right? And you imputed 5 times, right? You impute 5 imputation. How many missing? This is the missing value imputed 5 times. And the math had more missing value and imputed 5 times. So you get the imputed value. The function complete gives you the one complete. If you identify which one, you get like number third imputed complete case. So you said after you impute, you have as many as number of imputation complete case. So you can identify and get each of them separate. You don't have to, but you can look at that. You can look at the data to see, oh, for example, there is no 110 because nobody can get 110 right in this, for example. And then this is good. This is very good. If you know long and wide form of the complete cases, this is the way it is. You have the long form and wide form of the complete cases in one big data frame. So that is also very good and helpful. And then we can do analyze, right? With each of these imputation, run LM. And that gives you mirror, right? Fit is a mirror. Oh, print false doesn't print all those imputations. So if you do print, doesn't print. Any question? Any questions so far? So we get the idea, right? It's very simple. It's very beautiful. No. Again, the thing that I explained, changing the predictors. You can change the predictors. And then you see impute predictor matrix gives you that predictor matrix. And then you can change it, this pred, right? Initiate predictors is everything, predict everything by default. And then let's say for some reason, that reason you have to have a reason to say, okay, I don't want right to predict all those others, right? Row is the one that want to get predicted. Column is the one that is predictor. So if I do that, then I get all these values 0. So then right doesn't predict anymore. In a special case, we might want to do that, not always. For example, if that predictor is not correlated with those predicted value, probably you don't want to bother and use that because you're just adding a noise, right? So if the correlation of that is very small, then you don't want to select that. You can specify what correlation you actually is important for you. Usually 25%, 0.25. But again, it depends on sample size. It depends on your type of analysis. It depends on percentage of this. So those are things that is not a certain answer. I cannot tell you like use all the predictors. Is just rule of thumb. It says like 25%, 20%. Yeah. So that's for that. As you see, when I did that, then this one doesn't predict read because there is not much relationship. You saw that in that plot I showed you, like this 2x2 two-way plot. That is the reason. There was not much correlation. So, and then there is this function, quick prediction, which sometimes you have a remember, a lot of time we have a big data set and we have many variables. And that's why there is a loss of missing. If you have a small data set with not many variables, and there is not much correlation there, it doesn't do much good for you, right? The power is when you have a loss of sample and you have a loss of variable, and you can more precisely predict the missingness. Okay, now I talk about that iteration, and then the fact that this imputation should be independent. And I talk about that Markov chain, right? And I said that this Markov chain here is a little different because there is a level of variation that added to that imputed value that doesn't really need a lot of iteration. So basically, you don't want to see a pattern here. You don't want to see this goes like, remember, this is the iteration, x-axis, right? So you don't want that iteration goes up for everything, right? It goes up and goes down at some point. So then you need to see that iteration. So again, let me explain it this way. These are the parameters that you use to impute the predicted value. To impute the predicted read, you need the mean of read and you need the standard deviation of read. Basically, you need a multivariate normal mean and standard, so to get the random predicted value for all of them at the same time. But again, it does run through a chain of equation. So it impute each of them separately, but it doesn't mean they are independent to each other. But as you see, if you see some sort of trend, they are going up together, down together, or things like that, that means they are dependent on the value before. So maybe this is not enough iteration to really see the pattern. So you can add always number of iteration to your existed values. So let's say we went up to 10 and we want to add like another 10 or another 50. So it starts from here. It doesn't, you don't want to go back, and you can start from here and continue. So basically this can be drive, this can be get, you can get that directly from Rice and by hand plot that, but just plotting imputation gives you this. So, and again, 5 imputation is 5 imputation. 5 imputation for each of those variables, right? So that's why you get 5 different parameter set for each of those variables that gets imputed. Yeah, these are all the methods. You see, many methods. And then I don't know all of those. There are like some classification regression trees, which is kind of like non-parametric way to do random forest imputation. So you can have all those type of imputation. And this tells you the type of variable that you want. So those works for any type of variable, continuous, discrete or ordinal. And this tells you like what type of variable: ordinal, use polar, log, reg, binary, logistic regression, and quadratic terms also included, and things like that. And by method mice, you see all these methods, and it tells you what those are mean. So now let's say we want to change one of the imputation to Bayesian normal linear regression. So it's not predictive mismatching. So I can change it to norm, So that would be the using prior and posterior normal for y, for right, to get the predicted y. So basically it does that. I think is the parameter also is normally distributed. Not all of the parameters, the mean, but the prior posterior of a standard deviation has different distribution. We are not going to talk about that. But that is in the Bayesian. There is like inverse kind of like inverse chi or something like that distribution for a standard deviation. But anyways, yeah. So as you see here, I change only the method for right to normal. And then I did the prediction and I ran it again, right? But this time with this method. So I can run it for only maximum iteration 0, only to get that, what is the methods. And then you don't have to, this even don't run. It gives you this result, and also it gives you what predict what. So I change the method to the new updated method, and then I get this imputation and then the plot. Let me see. It was math. Right. Mean of right. You see, these are very spread, I would say, but these are not. It's not much independent, I would say. Like everything goes down together, right? So it's a little worrisome because I don't use predicted mean matching. So basically, probably I need to run more iteration for this one. So here I did the more iteration. So you can just, you see, this IMP was the missing imputation data set. It wasn't data frame, right? So I can run a function called mice-meets. That mice-meets doesn't like, doesn't need data frame. It gets the meets object, adds the iteration to it. So before I had 5 of them, by default was 5. Now I add another 45 from the last one. So it started from here, right here, 5, and then it goes up to 50 iteration. And now you see there is not much, it's very, you don't see much pattern here now, right? Even for this right. So that's why you mean of right, it still goes down altogether up. I don't know that, but I think it's much better than, you can run more iteration. You can have some burning at the beginning. So run the iteration like 100 and then run another 50. So those are the technique that we use in the MCMC. This function, strip plot, gives you some sort of those kind of investigation after you do imputation. So for the math, I can see that imputation number 1, 2, 3, like 1, I think it probably is a non-missing. But you see those imputation, those red values are the imputed value that you can see is among these kind of have the same distribution as the data itself. So it's good because you don't want to see some data point that is very high or very low or very scattered some point or things like that. If you do that, a strip plot for all the variable, you can see this is good. This is basically this plot in another way. And they do jitter to see the difference between this point. Look at that. Right. We didn't use predicted mean matching. That means we just randomly predict those values. And then you can see there is a lot of values that are not maybe plausible. It's very rarely there is a lot of these people. So that's the thing. Now you have to think about what happens here. And those kind of the sensitivity analysis that you can run to check for that missingness and things like that, right? So now, this part, remember when we pull the data together, we have like 5, 6, 10 analyses, and how we get the variation, how we can implement the variation for those parameters. So in here, I talk about the mathematics that behind of those computing the standard error of the combined result. The estimate is easy. You just average all the estimate for that quantity or that statistics. That statistic could be the mean value, could be coefficient of regression model, any parameter that you estimate. You can average that and get the combined estimate. So basically, this is what I mean. Yeah. So basically, I mean that when I haven't pulled yet, okay? So when we pull them together, you get the estimate. I haven't talked about pool yet, but before I wanted to talk about how you get the pooling. So basically, yeah, for each estimate, you get one Q, which is that Q could be beta 0, beta 1, or any quantity that you are interested to estimate. And this Q bar is your pooled estimate, right? Very easy. That part is done, right? Okay, now, what about the variance of this Q bar? The variance, they said, has many components. There is a component, they call it U, which is the variation within each of those imputations, each of those estimation of the imputation. So you run the regression model for each of the imputed. Each of them has a standard error of that Q or that parameter, single standard. So you can get that U from averaging all these standard errors. So they call it within variance, or you can see it as a within variance, right? Within imputation variation. Uncertainty that comes with that imputation, that single imputation. But there is uncertainty between all these imputation, right? That calls B, right? So basically what you do is you can compute that from this formula. This is very sample variance, right? Remember, xi minus x bar divided by n minus 1. This is the same thing. So you get the between variation because each imputation gives you different estimate. So you want to see the variation from imputation to imputation, right? Each imputation has its own variance, which is this uj. And then we average that to get the average of the within imputation variation. And then we get this b between imputation. But there is another correction factor here. And this correction factor, you can think about it. Yes. You have a question? Sorry. I will stop after this to ask questions. This 1/m is the correction of this b because remember when you want to calculate a standard error, this b try to estimate the variation between this imputation. But that between imputation variation depends on how many imputation you have. If you have more imputation, you get more accurate estimate. If you have less imputation, you have less accurate estimate of the imputation to imputation variation. So this 1/m basically is the correction for that between imputation variation. So that adds there. If you have many imputation, this becomes 0. So you have a very accurate estimate of between imputation variation, right? So think about this. We want to estimate this uncertainty. So if you want to estimate uncertainty based on 2 data points, or 10 data points, or 100 data points, your estimate is getting more accurate if you have more data points, right? So basically that will correct for that a small number of imputation, if you have a small number of imputation. And then we add everything together to get a total variation. And that total variation is total variance. And you of the parameter of this Q bar. And then you square it. You square it. You square it to get the standard error of that combined estimate of the parameter. Make sense? So that's a basically idea about this adding. But what is important here is that you want between imputation to within variation to be a small number. So this gives you some measurements of relative increase of variance due to non-response. If you have a lot of non-response, between imputation variation is going to be large. So compared to within. So basically you get a measurement of how basically good is that variation of the imputation. So basically how much addition of variation that missing data causes to us. That will gives you some sort of idea, some measure about that. So also you can define it this way, divided by t instead of divided by, so this is r hat is some estimate of relative increase due to non-response percentage compared to the within. This is the proportion of variation, very similar to r squared, right? You can think about what proportion of variation is by the missing data. And that gives you this. And this value is always between 0 and 1. And it's called in some literature approximation of rate of missing information. Basically, kind of give you what is the rate of missing information in fact. And then another thing comes here is that now we calculated this total variation and this estimate. Is it fair to use the traditional T distribution with the number of degrees of freedom? What is the number of degrees of freedom of this Q bar? Basically, that's how you calculate, approximate that adjusted number of degrees of freedom by this formula. And then there is a like modified, adjusted, and things like that. And there is another, yeah, you calculate this, and this V hat basically comes from this formula. So MICE does that for you. But the idea is to understand this, the reason I showed you this, to have you understand this kind of what's going on about the uncertainty, and think about uncertainty and how this missing data create extra uncertainty that we need to estimate and add it to that combined estimate, the standard error of the combined estimate. So the last step, we pull them together. This is easy. So that's why it came last. So you get the fit, you get the mira as a matrix, and for each of those mira, you can get like which analysis, like number 2 analysis gives you this is basically kind of a list. And then you do pool. If you do pool on mira, you get the MIPO, right? So you get the pooled information, and if you do the summary, you get all these results, the terms, the estimate, the standard error, which is that total standard error. You get the statistics, this divided by this, and then you get the degrees of freedom. And these degrees of freedom gets closer to 200 if you have less missing. So if you have more missing for that variable, that gets close. You know, it depends on like the amount of missing, amount of uncertainty, and it kind of measure, adjust for that. And then you can just print this and get some other information, and you see those terms that I talked about, Y bar, U bar, I'm sorry, U bar, within imputation average. Basically, this is average within imputation variance, right? And then this is the B, and then this is the total, right? You see all of them are here, right? This is the variance, right? You take the square root of this value, you get this value, right? The square root of this variance gives you this standard error. And then degrees of freedom for complete. If you have complete, now you have the degrees of freedom. You have this R, you have this lambda, and this you have it's called factor of missingness or something, some other measurement that I think I showed you in this formula, but I'm not sure. I need to look at it again. But lambda is the lambda that I showed you. This is the R. And I think this is the percentage or something. But about this, I think is this guy. No, not that. No, I'm sorry. I think this R lambda I showed you, missing information. Is something like that. Do you know, Andy, what is that one? I'm not sure. Fraction of missing information. Sorry, got it. So that's the reason I do. So this one is the fraction of missing information, and this is the related increase. I think. Still not sure, because there is one comma, there is R, and here it is R and then lambda. There is some sort of adjustment, but it's related to this. Any question so far? We are almost done. There is one exercise that we want to use mice to multiple impute HSV2 and using this variable. Remember, these variables are factor, is categorical, female and program. And remember, this variable doesn't have any missing. But this variable has a correlation with the other variable that are missing. So that's why we want to use that. But we don't impute it. Mice automatically understand them. So basically use this data set, use these variables from this data set, run mice on it to get missing MIDS, and then run the analysis on all the missing. Maybe you can run it for like 5 imputation or 10 imputation, and combine the result used tool. So I give you like 5 minutes, is that okay? And then I will answer your question. I actually show my R. Let me see. And yeah, this one. So basically, I want to get for this exercise first extract the variable that I want to include in the missing. You don't have to. You can use all of them, but make sure those variables are not like character or things like that. And then you can just set those predictors to 0. But here I get it. I could use select in package deploy R, but this is the way you get the data for this exercise. I put it in chat. And then next step is using mice, and then you can call it impute, and then add, and then mice, and then you can define. Let's do it for max iteration of 50. Even 10 is fine, but 50 and 5 imputation. You can ask question if you have any question. And please, before I forget that, one more time, please click on this link. Oh, this was the impute mice, and then this link. Okay. Again, the good thing about mice is it's very robust in a way that it runs and you know, like other methods, sometimes they don't converge, sometimes they complain, you know, like the variance is not positive, definite, things like that. Very rarely mice complain about those kind of computation. Computationally is very robust because it used Bayesian. So kind of running is sometimes might be slow, but and it go and use the chain equation, so you can implement different type of method for each of those variable you want to impute. Those are the good things about running mice. Oh, one more thing that I seen a lot is you have to be very careful. If you have a categorical variable with 50 category, that would be very dangerous, because then you have tons of parameters to estimate, and that causes a problem. Be careful on that kind of type of, unless you have like 5 million data sets. So you need to consider those kind of technical issue, same as any kind of prediction and predictive modeling. Probably you want to run as a non-parametric methods if you have those kind of cases, but yeah. Any question? Yeah, you can ask. I think Andy handled all the question very well, so he didn't left any question for me. Okay, we didn't leave it. So let's run this analysis. So I actually did that. Now I do mice, and then I said, okay, m equal to 10 and max iteration equal to, you see, the good thing about RStudio is when you type the, and then print false. I don't want to print it. And run it. Now it takes time because it's like 50 iteration and 5 imputation each. I don't think this takes a lot. Yeah, that's it, right? Even with this many iteration and imputation. And then I run this. And then now you look at the methods, right? Polyreg and logreg. Logreg was binomial. Polyreg was multinomial imputation. So because program is different program and is not ordinal. So, and okay, this method is here, this method for social science. No, yes, social science score. This predictor is empty, is blank. That means this doesn't get predicted. If you don't want to predict a variable, make sure you is not enough in the matrix. So if you look at this one, non-variable, everything predicated. If you, I do, first of all, that, yeah, here, this is the variable. But you see this variable doesn't get here. It gets predicted using all variables, but because the method is this, it doesn't get imputed, okay? Because it's already imputed. So if you don't want to impute that, if I put all this equal to 0, what happens is it's imputed based on the mean of that variable itself, if it has missing. So that's not enough, okay. Because we had a client came and she had this problem. And then we figured it out. But that's the issue, that even if you don't want to impute, if you put that method, that predictors all to 0, you have to put the method also to empty. And then you can plot. Looks good, right? It's going to where there is no pattern. This is our female, right? The female variable is not technically normal, is a little different, because this is also like, you see the value is between 0 and 1. That's why, you know, that's the reason. But anyways, but pretty much, you know, is going up and down, up and down. And then I do pull and then summary. And that gives me the result, the final result. So I get the standard error. And then if I print pull.fit, I get those extra information about U bar and B, between, within. And these numbers looks pretty good. You know, they're very small. This is the degrees of freedom adjusted. You see that because we are including many variables, then we have to be very conservative for some of those. So yeah. So basically, this is how you run a multiple imputation in mice. If you have any question and want to ask, you can go ahead and ask. Other than that, you are going to stay about 5 more minutes. It's 4.